And the first speaker this afternoon is Holger. No, it's not. It's, it's Per Siegbahn.
Right. You recognize me?
Yes. Per and I have been good friends for many years.
Sure.
Ever since I started looking at photosynthetic structure, he's always coming around and saying, "Can you see the manganese complex?" And it's been a wonderful journey with him.
Sure.
And when we first modelled the manganese cluster, we modelled it as an M404 cube because it fitted quite well. But then we realised from anomalous diffraction data that there was a calcium there, so it had to be a distorted cubane with a calcium. Now, would that be a stable molecule or not? If you take out a manganese and put in the calcium. I went to Stockholm, saw this gentleman, I had done calculations on MN404, and I said, what would happen if you put a calcium in instead? And I went away, and I saw him next day or a few days later, and he said, well, it actually will be stable. There'll be some changes in bond lengths, and that was very important to me. So it was fantastic, and it was a fantastic time, and now we're still on the job and trying to sort this whole thing out. But the structure we're pretty good on, aren't we now? So,
okay, thank you for the introduction. I'd like to start by thanking you again for organizing these meetings, and Bertil, who's not here, but I will see him tonight.
You've got a microphone on, haven't you?
I think so.
They were complaining that people weren't putting the microphone on.
Well,
Yeah,
should be okay. So I thank you again for organizing these meetings. This is, I counted the times I've been here, and I found 6. And I heard there had only been 5. But apparently there was a meeting before which was not considered an Oriental Bunty, but a similar subject.
Yes.
Looks as I was there. I've been to all of them, otherwise. All of them, yeah. And some of the others have as well. Okay, so I will speak as for Jim wanted it, so I speak about water oxidation. I have other themes to speak about nowadays. I work mostly on nitrogenase, but nothing about that. So this will be a review of general things, other things I've done mostly since 2006. I would say before 2006, the only thing that came out was basically that there must be an oxygen radical somewhere, which was clear even for otherwise you need a structure, and we got GM structure, and that started everything off. When we do calculations, these are the rules. The most important thing in the calculation when you do Solver-Schrödinger equation or in DFT form is the energy, which seems quite abstract for an experimentalist. It is measurable only in principle. You have to stripe off all the never done more or less except for atoms. But the interesting part is, of course, energy differences. And you can then, when you have energy difference between different structures, each structure gives an energy. So you test 2 structures, and they differ by 3 kcal. You're within the error bars. Can't say anything. It's already about 5 kcal. My experience is that it's unlikely that the higher one applies. And when it's 10 kcal, you can say safely now that this cannot be the correct structures. This goes also for transition states and short-lived intermediates and so on, where we have our advantage with calculations. So I've done water oxidation since 2000, and so, as I said, only the oxygen radical came out of the first years. Then I worked on the mechanism which interested me most. And I have a mechanism in 2006 I will talk about. And then structures, I went after the mechanism, which I felt has to be the right one. I went to structures to make better structures than were available. And then you have at the end, you have the full energetics in terms of a diagram. When you have that, and the calculations are right, you have everything. This is the goal of every study of a catalytic cycle, that you have energy level. So this was 2013. I did minor investigations since then, that's 5 years ago. So I will mention a little bit of that, but not much. When I started 2006, there was the structure of gym structure, the Ferreira structure, looked like that, sketch. Some year later, there was a structure by Lon et al., looked like that. When I got this structure, I took these, added water to them, calculated pKa values and binding energies, and I ended up with one like that, which is much better in energy. This was 2006. And from this structure, I knew there should be an oxygen radical, and I decided the way we do it is that we do all possibilities. We don't care what people have suggested. We take everything possible. So put the oxygen radical where it's possible, and you check the energy, and then you find there are basically two places. And then you take all the oxygens that could connect with it. Many of them are waters from the outside in the nucleophilic attack. So this mechanism where you find the oxygen radical, is it here? Yes. And the bridging oxo that makes the bond has stayed basically the same since 2006. There is a variant of this, extremely similar, where this hydroxide connects with the bridging oxo. As a very similar barrier, so it involves the two same manganese and the oxo in the middle, and so not surprisingly it's very similar. So that was it, and I continued to refine it, and the latest calculations I did was 2013 with a much bigger model, and you can see it looks very much the same, the oxygen radical here and the bridging oxo here making the bond. And the reason this is a very much better mechanism than anything else is that you have to look at the spins. If you look at the spins here, you have to have anti-ferromagnetic coupling between two manganese. In this way, one binds the oxo, the other one binds the radical. The oxo can lose an electron, a blue one here, to make manganese 3. It has to then to have the same direction as this one. Then you have the red and the blue on the oxygen, and you form the bond. And this can be done very smoothly if you have this arrangement. You need two manganese, and you need to have antiferromagnetic coupling, and then you got it. And this you can't have a nucleophilic water attack. So I more recently was surprised that this mechanism with the nucleophilic attack was still alive. So particularly for conference in Innsbruck, I decided afterwards I need to look at this again, because I thought I had already shown it doesn't work. But this was a long time ago. So I looked at this again, very similar, possible positions for oxygen radical. Turns out that these two are the most stable ones in S4. And then you connect everything. Now you look at this case water attack, so you come in with the water here. It can do it in several ways. And I did all of them. I don't know of any other possibility to do nucleophilic attack. And as you can see, the oxyl-oxo barrier importantly, from the S4 state is very low. And from the S4 state, your nucleophilic attack is extremely high. So with the rule of 10 kcal, this has a big margin of saying that nucleophilic attack is not possible. And the reason is that the product is very unstable. Maybe it's arranged that way to avoid hydrogen peroxide formation. But it's really easy to say that all of nucleophilic attack cannot be possible. Say with high certainty. So the same thing again, the barriers in this case and should be repeat. It was, as I said in the beginning. So this nucleophilic water attack is impossible, and the reason is very high in any. And then I haven't heard of any other mechanism which is suggested which can be tested. So I did structures, and now What I have here is the S0 structure and the S1. And here I have 3 manganese 3 and 1 manganese 4, electron and proton. The proton goes from here, the bridging hydroxyl. Electron goes and it goes from here. So you oxidize this one. In S1 to S2 you oxidize this one, but no proton leaves, which is known a long time by Wolfgang among others. And then you have the S3 state where I add this water here, which becomes deprotonated. Now, the full mechanism, I have a slide from 2009. So I have this sketch of this is the S0 state where you have already bound one of the substrates here, or one of the waters rather, and deprotonates here. This is the end sort of when you have produced O2. So directly water comes in and deprotonates. Then you take away electron and proton, and you oxidize this one. The proton goes away, and now you have just the S1, and for to S2 nothing happens basically except that the electron goes. Water comes in, it ends up here in the middle. There's actually a good space here. You don't need to open up very much to get the water in. It's almost the same space. And then you can, in the next stage, you create a radical, and then you bind O2 this way. This is very similar to what in 2006 and also all the way up to now. So this was suggested now close to 10 years ago, which is amazing. It took a while, and then the first experimental confirmation came. I should say that in this very place, I said that the structures until then must be wrong. Did it here? Wolfgang was chairman and said that was a very outspoken talk. Oh, was it? And it took only a few weeks before Yan Shan came with this structure. And the most important part here for me was that he confirmed this oxygen, which was not in the other structures, and the double bridge to this. So that was, of course, very important in to be convincing and so on. And some later, Shen came with an X-ray free electron tracer study where things move a little bit. It's slightly different from the DFT because there is maybe a protonation here, which could be there or not, very similar in energy. So there's no problem there. And then there was spectroscopy started with the Lubitz Messinger groups in Mülheim. And they did the S2 state first, see a lot of EPR there. And they could, or everything in red, they could confirm from my structure. So the position of the manganese 3, the other ones are manganese 4. There is an oxo, which is a substrate. It's this one, which I had. There's another oxo here, which is not substrate, etc. What else? There's an hydroxide here and the water here, which comes to be some of the uncertainties here. They are, if you switch hydroxide to water, energy doesn't go up so much. The S3, this is the S2 structure. You can see there from the EPR and spectroscopy, Johannes spectroscopy and Nick Cox. They are practically identical. I should have added one thing, is that I had in 2008, I had this carboxylate and aspartate sitting here, and I had this hydroxide here. So I had to switch place. That's, as I think, the only thing that differed. And switching place between the hydroxide and the negative carboxylate doesn't do anything to the chemistry, so the mechanism remained exactly the same. The S3 structure took a few years, and then the same group of Lubitz suggested this space. This was the one that survived from spectroscopy. And this is my structure. And You can see that's very similar, and they have this hydroxide here. And they also suggest the same oxo as a substrate as I have. Now, everything looked great until now, soon 2 years ago, there was an X-ray free electron laser study which showed that there is no hydroxide here. The resolution was claimed to be high. So what is the problem? I cannot say exactly what was the problem. I can only say that there is a problem, as I will show. I have this hydroxide here in S3, which is, look at it, obvious from chemistry. You need to have 6 coordination here, which this structure doesn't have with a long distance here. So there is a possibility of a radical, but so I did again all possibilities I could think of. Here is one with all manganese 4 and with a missing hydroxide, very high compared to my structure. The oxygen radical structures are even higher. So I can say that, I put it this way, the structure they gave is not an S3 structure. Doesn't matter the formulation, but it is maybe an S3 which is completely wrong, or something else. It's not a real S3, the real S3. In the meantime, the X-field structure was done by the Berkeley group, and they had cooperated just before with another person doing calculations, and he obtained a structure which has similarities. It's not really the same as the ones I have here, because there are 2 short bonds, and this you can imagine that you have. But this is the problem here, is that it was not done in the correct way. So they left everything moving around, and that can give very strange results. So some ligands moved 4.5 ångström and so on. So this is not a reasonable calculation. Another thing that has come up here is in recent years is that the mutations of the valine here was discovered by burnup, and that it strongly affects the water oxidation. So it means to me that the water must come in this way. And I checked that, and it doesn't come in unless you rotate the valine. Interestingly, the valine is present in many enzymes. Cytochrome oxidase, you have one, and also in nitrogenase, there is one directly over the active site, which sort of sorts out the correct substrate. If you make it bigger, it stops. If you make it smaller, other ones come in, unwanted ones. But to do this, nobody has been able. I tried, and it worked for a year or so, and it's this one rotates, and a lot of things move here, which is a little bit outside the specialty of the methods we use. Then I have as I said, the energy diagrams. This is this contains everything. So here is, in my view, the full understanding here. Where you remove electrons and protons, and from this, if you like, you can read the pK and redox potentials in each step. You can see where the water comes in and where the water goes out, etc. And you're all the way up to formation of O2. And you can calculate the barrier, which should be counted from this one to this point. So it's not, the barrier is not from here to here. As I heard in a talk recently, that is not at all the case. So the real barrier, so if you want to do isotope effects here, it's not enough to look here. You have to look here what happens as well. And this one doesn't matter at all. So these two. I have considered also including tyrosine Z, the oxidation, in the diagram. And I obtained the full diagram like this. All of this is presented in the book by which Morten edited. So everything is there. So I assume a loss, which to me, initially I felt that this is lost. You just have a driving force to get to the tyrosine radical, and that is gone. but it does not affect the rate-limiting barrier very much, less than 1 kcal. So apparently, but it raises it a little bit because of this energy you lose. So what it must mean is that there is some advantage with losing the energy and going through a step to tyrosine radical, and probably this has to do with preserving charge separation and reaction center. It makes this step very much faster because it can go all the way to tyrosine than if you have to do the oxidation of the cluster, which takes long time. So this is a way to quickly guarantee the charge separation for a millisecond or so. And it does not cost much. And we have the role of calcium. To look at this computationally means that you replace calcium with 2 protons. You never change the charge in an enzyme, so you have always a proton. I mean, in this type of situations, you can do it temporarily during proton transfer, etc. But here, if you relax everything after removing calcium, you can be sure there are 2 protons there instead. So I do the S1 to S2, and it works easily. You can do it, this step you can do very easily, just as you do with calcium. But when you come to S2, S3, you find that it's very easy to remove a proton, but correspondingly difficult to take away the electron afterwards. These are very similar energies, and the sum of them are nearly 0, which means we have actually from here, the proton coupled electron transfer is really just breaking a bond. Nothing else is changing. The charge distribution basically the same. So breaking a bond is the only minor effects of from the surrounding, but taking away the electron has enormous effects. So here I can see the experiment says you can go here, but from here you cannot go. It stops if you take away calcium here. And here is the reason you have the redox potential, and completely independently, Theodore Agape found similar things for biomimetic. So we are really united here on the reason for this type of calcium in. And then I'm almost done. So the conclusions remain essentially the same. Few things has changed. This remained the same. There was this modification I said, taken from Shen structure, that the carboxylate is bridging rather than terminal. And in my view, there is full understanding. But this is, I want to say that this is not a lucky shot. I mean, we have done many enzymes, and now we are doing, rather I am doing, nitrogenase, which is also extremely complicated. And there are no indication that it shouldn't solve the problem. And I think all redox enzyme, the mechanism of this type, can be solved by similar type of calculations. Not all types of calculations, but the ones we have developed. And I think that was it. Thank you.
Yeah, thank you very much for your lecture, but also thank you for giving us some time for discussion.
Okay.
Perfect. I was worried.
I give this faster and faster every time.
I'm sure there's plenty of questions, so let's check.
Per, you showed us the key step for oral bond formation. One is oral 5 with oral A.
Yes.
That's called oxo-oxo radical coupling. But also you said it's possible with oral 5 with oral B.
Yes.
I was wondering what is the energy difference between these two.
I mean, the barrier is 2 kcal difference or something.
So it's not big difference, right?
No, and I said when we did it finally, I mean, I did this already 2006, and then I changed to the other one 2008, and the difference is small, always small. It is very similar, and Johannes has suggested the other one, so which is fine for me. I don't know, to me they are extremely similar, and I cannot really differ.
I'm very happy to see this because recently we figured out a new proposal with the key step also involved oral 5 and oral B.
Okay.
So I'm
Yeah.
going to present that tomorrow. So I'm
All
very
right.
happy to see you said
We
2
did it.
kilocal per mole is not so big a difference. Yeah.
No, I did 2006.
Do you want a question, Gary? We're trying to move on as soon as we can because of the time, because we
Yeah.
could be here hours.
Yeah,
discussing
Per,
that.
I just, this probably sort of jumps the gun on Victor Batista's talk, but he's done calculations now that show that a nucleophilic attack mechanism has a very reasonable barrier.
I know it's wrong.
Yeah.
So he doesn't know how to do these calculations. I mean, there is, I mean, for one thing, he says that the barrier I have is too small. Ridiculous. It's not too small. It's perfect. It's a millisecond. And he said it's only 6 kcal because he counted it from another intermediate level. And things like that. He has QMMM, which gives enormous effects, which never
Well,
happens.
the second thing from Victor's results is that the protein itself is surrounding the manganese cluster. And they find that in order to remove protons from manganese 1, that there has to be a water positioned in there, and that is sterically occluded by the protein. I mean, your DFT calculations, you just include the cluster, but not the protein.
Oh,
So the
if I do it correctly, I
barrier
should
that
have
they
these
calculate
waters.
is actually very high for deprotonation of the water on manganese 1.
Yeah, I mean, we have tried this, and we have water molecules around, and we move the proton over to this.
Yeah, I know, but you don't include the protein that surrounds the cluster.
That we have enormous experience that this doesn't matter much, unless you go to the real border. If you want to
It does matter if the waters that you put in are blocked by the protein side chains.
I doubt it. Okay.
Victor's going to give a talk, I hope, a live talk. But he obviously said you were here, and he's a bit scared of being here. Billy.
Just a quick question. So, as in many systems where you transfer a proton, it's quite important also to consider the energetics of protonating the acceptor. So, in all these transitions where your proton goes somewhere, what is your acceptor?
The acceptor is the bulk. And
Okay.
the intermediate acceptors can of course lead to barriers, but this
Right.
is very unlikely because every protein almost transfers protons.
But
And it
isn't
does
this
it in a
a
way, and
key,
it's-
like for example in oxidase, that you have a loading site or something which actually is part of the barrier or preventing
And
it from going?
proton pumping is very different.
Sure,
But
yeah.
proton transfer is a simple thing.
Yeah.
No problem. It is always in all
But
enzymes,
deprotonation
even,
is
diffusion.
linked to the acceptor site as well.
And in cytochrome oxidase, this may be a more important issue. It's not important here.
Okay, thanks.
Alan.
Yes, as you know, in most of the work,
Hang on.
in most of the work, people involve a transition in S2 between a low-speed state and high-speed state with a closed open form from the manganese cluster. This kind of transition does not exist in your model. It seems to do not exist. Do you have a comment on that?
Are you saying that the water that comes in S2 to S3, or?
So I say in most of the computational work, you need to be in the high spin configuration in S2 to go to S3. In your model, it seems this is a low spin configuration you have for going to S3. And you never involve high spin configuration, but do you
It's
comment?
actually the opposite. I have high spin
High
configuration.
spin,
For
but,
all, I
yeah.
have total ferromagnetic coupling, which
But
is
you-
not right.
This
I
is
mean, it
seems
is an
to-
approximation. So it is tested. I mean, all the spins are parallel on my manganese.
yes, but the structure of the cluster is not does not correspond to what people call the high spin and low spin.
Oh, I see.
It's,
Yeah,
you
well,
say
okay, that
You
type
have
of
a between manganese 3, manganese 4. You have a dimioxo on your structure, and that is not the high spin configuration that people
Oh.
involve. So
these
it's
things
very
matter.
different from your model.
Yeah,
from
I
this
mean, I
point.
checked a lot on
Could you pass it
on
behind
this,
to
and
the
it
young man here?
doesn't it doesn't matter much for the energy, so it's not an important factor. If you want to look at spectroscopic details, this is important. I never did that, so.
Another question.
So Professor, you don't prefer water nucleophilic tag mechanism. So what's the case? How do you think the case of the reactants as hydroxide rather than water?
From the medium. If the hydroxide comes in and attacks, you mean?
Yeah, yes.
There, this is high energy.
Also high energy.
You have to create it first, and this is to create the hydroxide is rather expensive. So you have to pay that price. After that, it's very easy to do the attack, but it costs much.
Okay.
No,
Okay. Now, Johannes. We've still got a few more moments, so let's go for it.
I have one question. I think we discussed it earlier already. In your mechanism, in those two states, the fast or one of the substrates is not bound. It actually binds when you come to the 3 states. So
Yes.
that seems to contradict the water exchange experiments, where you have both substrates already bound.
So
in
this
those
is
two
why you
states.
prefer the other very similar mechanism. I cannot argue against that. This is possible, but it has the same barrier and it involves the same. So this is
As an old inorganic chemist, I have a rather general question.
No, you're not old, you're young.
How well does DFT work on transition metals? There are lots of inorganic crystals, mu oxo-bridged manganese. So you could very easily test your method on
Right.
available. Have you tried that?
Oh, yeah, I mean, this is a good test, isn't it? And I could, I mean, I did a lot of calculations around to say, so I could strongly go out and say, this is it. I didn't do it just by hoping, but done a lot of other. There are complexes, even small ones, particularly small ones, can be much more difficult because you have complicated spin couplings with the d electrons. Here is now, when you saturate, the spin coupling is much simpler in these systems. And they are also high spin coupled on the d electrons, which is also makes it easier. And it is the case for most enzymes that d electrons are high spin.
I could maybe comment on that too, because Victor Batista has worked with me a lot on small molecule calculations. I think in general DFT gives very good structures, and I think that you can rely on. But there are sometimes cases where the energies can be way off. We had a trinuclear manganese cluster where the ground state was predicted by about 20 kcals per mole wrong.
This is usually wrong again because I mean,
And so
if it's so
sometimes
wrong,
there are cases where we get the wrong answer for the energies.
there are many ways to do calculations incorrect.
I have a question because you say you calculate the energy, but we know the energy is strongly dependent on the charge. I want to know either in your S2 or S3 or S4 step. So what is a neutral charge? It's a the charge. What about the charge?
The whole complex.
The
Sure.
whole complex, yes.
Yeah. So we did a few, and I did a few, and this is the one that I could compare to various experiments to say that the charge I use here, I cannot remember, is the one that makes sense when you compare to the mechanism.
So if the charge is different, the energy makes huge difference.
Well, the relative energies do not matter so much for the charge, but there are differences, and the other charges are not reasonable. Does not give reasonable energetics.
So my point is, in your S3 state, it's a without charge or with charge. In S3 state,
If I have charge,
yes, the positive charge or
I have charge in all of them, but they have -1 or something like that in all. They are the same, have the same charge from beginning to end, except you remove the electron, of course, then it goes to 0, and then removing a proton, it goes the other way, etc. So it varies by 1 unit, which is always the case in redox. There are temporary steps where you change the charge.
Okay, Wolfgang.
A question on, it follows Rudy Marcus, yeah? How far is theory predictive or not? You were kind of predictive on a structure that was almost right. You had small modifications. But now my question is, if Jim had not published the structure, the original one, could you have dreamt of a structure by using DFT?
I was dreaming about it, and I failed during 3 years.
Dreaming about it and contacting me. I missed an aeroplane once.
I mean, a starting structure, the gem structure, was very important to go on, but it doesn't have to be
You're
perfect.
saying it's wrong. I don't like that.
It doesn't give the right mechanism.
You
have the wrong.
He took the structure and he refined it using
No,
DFT.
I
And
don't
he did
think
a
so.
very good job. He even predicted
If you
the
take your
extra-
structure, it doesn't give a
Keep
good
getting it
mechanism.
wrong.
Yeah, it's wrong.
And they should quite rightly say couldn't have done it without it. So.
No, it's a very useful start, but it is still wrong.
No, we're all claiming it. You see. Okay, who's a new person? You're a new person to ask a question, yeah.
Small question. At S3 state, what's the valence of the manganese atoms, ions?
In S3, they are all
Yeah.
manganese 4.
All manganese 4.
Yeah.
Do you think there's any other possibilities?
Yeah, we have tried a lot of possibilities. We've been suggested a radical and one manganese 3, etc., but they are all high. We never see a low-lying state there.
Okay, thank you.
There is an accumulation of a positive charge, I think, between S1 and S2, because we lose an electron but no proton.
I have that.
There's a positive charge collected in the cluster. Where it actually is, I don't know, but it adds to the overall oxidizing battery, oxidizing potential of the.
I think it's more complicated than that. I mean, I've done.
You don't take that into account, do you?
I do, yes,
you do?
of course. I remove only one electron, so the charge changes in that step. But the importance of this, I fail to see. When more calculations I do, I cannot see the
Well, it depends on the mechanism. Now,
Yes, okay. I come back on my previous question.
Okay.
When you simulate the situation without calcium by adding 2 proton instead of
Yeah.
calcium, and you say, okay, you have you can go to S2 but not to S3. What is the spin state of your S2 in this situation? Because I agree with you, we cannot go to S3 when we have no calcium experimentally. We have S2 YZ dot. But the S2 is low spin in this, in this situation.
This may matter a little bit, but it is not the reason. I mean, there's different spins here. I mean, it is clear. If I want to do that, I have to check all possibilities of couplings. It's very possible I can do it if you
But
have.
in your calculation, what is the situation for S2? What you show here without
I
calcium?
always
You don't know?
have the same approximation that the spins are parallel for all manganese, and I've done a lot of calculations where I try other combinations which lowers the spin and didn't make any difference as far as I could see.
okay, I think, well, there's so, you can't.
What's
Oh dear, I hope it's a real deep question. Go on, go on. You're not going to say, is it coffee time yet?
It's just because there have been many mutants. I've discussed this.
Yeah.
With many mutants made, and Rick Davis is around somewhere, and he's for instance, the H332E I think is a good mutant. It blocks the S-state cycle at a particular point in the S-state cycle, and therefore that is a good test of your
I
method,
know,
because
I've been in
predicts-
contact with Rich on this, and once upon a time I hoped that I should be able to show this. It turns out that mutants here make enormous structural changes, so it's like starting from scratch. So it's not a simple thing. So I ended up doing a lot of calculation and never come out of it. So.
It's amazing, really, that if that makes such big structural changes, that our friend here from Beijing has prepared this cluster in an organic solvent.
Yeah, very amazing.